In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 2, Stress Analysis, Part 10. So far, we have obtained different functions for the general state of stress, for the principal stresses, for the deviatoric stresses, and for the invariance as well. Now I'm going to show you different images so that you can imagine how in 3 dimensions the components of stress could be positioned. Okay, this is a general state of stress for principal stresses. Of course, here we have shown the principal stresses in sigma 1 direction, sigma 3 direction, and sigma 2 directions. We have some components of stress in here, which are sigma tau 1 2, sigma 1 2, tau 1 3, etc., etc. Okay, the difference between this sigma 1 2 and tau 1 2 is that we have these principal shear stresses like tau 1 2, which are sigma 1 minus sigma 2, but sigma 1 2 is sigma 1 plus sigma 2. Okay, so here we have shown in a sphere in order to show different directions. Okay, different directions. For instance, in here on this meridian you can see the directions 2 3, because this is between 2 and 3. On this one you can see 1 and 2, 1 and 2. Okay, here 1 and 2, and here again 1 and 3, here 1 and 3, and so on and so forth. And depending on the directions, you can see the principal shear stresses and their values as shown in here. This is another interesting image which I have shown here. As you can see, we have this 3-dimensional cube here, but also we have some planes. We have 3 planes, perpendicular planes, which are sigma 1 3, sigma 1 2, and sigma 2 3. Okay, and this is the general Mohr circle. As you can see, sigma 1 3 in the plane sigma 1 3, this is in plane of sigma 2 3, so that's the smaller one, and this is sigma 1 2. Yeah, that 3-dimensional space that we showed you, we could project each Mohr circle onto a different plane and see, and we get the plane stress condition. For instance, here is the plane stress condition for sigma 2 3. Here is the plane stress condition for sigma 1 3, 1 3 here and 1 2 there, and all of them together we get the 3-dimensional Mohr circle. This is the octahedral shear stress, which is very important. And as you can see, we have this shape here. We have the base is the square and the sides are triangles. We call this a tetrahedron. Okay, this each of these shapes like that, we call it tetrahedron, and because there are 8 of these tetrahedrons, we call it the total shape, we call it octahedral. Okay, octa is for 8. 8 tetrahedra together form an octahedral. To further illustrate this For instance, this one or the other one, like that, you know, it's a triangle, and then it has this shape like that. There are 8 of these. Each of these are tetrahedron. We call this tetrahedron. There are 4 tetrahedron on the top and 4 on the bottom. 8 tetrahedron, we call them octahedral. As mentioned before, the cosine ratios are equal, and they are equal to 1/√3 for these planes, because they make the same angles with all the axes. Okay, so S octahedral here is square root of sigma octahedral tau octahedral. But tau octahedral, we could write it down as S squared minus sigma squared. And we had this relationship before. If we use this relationship, we get, because L, M, N are equal here, so we have written L octahedral, M octahedral, N octahedral, which are equal 1/√3, so that's S octahedral, and therefore 1/√3, and we get this. Okay, and sigma octahedral is sigma 8, because we said there are 8 tetrahedral together which form the octa. Octa means 8. So sometimes we use sigma 8, sometimes we use sigma octahedral, and this is the important bit. Tau octahedral therefore becomes this. Remember from here, because we have this sigma octahedral and we have this S octahedral. Therefore, we can write down tau octahedral equal to that, and therefore we have tau octahedral equal to tau 8, 1/3 sigma 1 minus 2 to the power of 2 sigma 2 minus 3 to the power of 2 and sigma 3 minus 1 to the power of 2 square root. Okay, so we call this tau 8 or tau octahedral. That's the shear stress on the octahedral plane. Now, if you notice that this shear stress is the one which is responsible for the slip, okay, and it's responsible for the deformation. Now, you will later on, you will see that in the yield criteria we use this relationship. Of course, you have used it before when you were studying your BSc, but you never realized that this is the shear stress which is acting on this plane. Okay, so if you have a crystal and the shear stress reaches that much, it will slip on the octahedral plane. And this octahedral shear stress, you know, this relationship is like that, and it's equal to that. So that's in terms of invariance, and that's it in terms of reduced stresses or deviatoric stresses. Okay, so J2 is equal to that, and you see this is a third of this to the square root, but J2 is equal to that. So you can relate J2 to tau octahedral. Okay, this is very important in yield criterions. Now here I have shown you the directions of principal stress planes, principal shear stress planes, and octahedral planes. This is the principal plane, principal shear stress planes, and octahedral plane. Now, this is LMN. Okay, LMN for the principal plane is 1, 0, 0, 0, 1, 0, 0, 0, 1. For the principal shear stress planes, the values are like that, and for the octahedral plane, obviously they are equal and 1 over root 3. Sigma is sigma 1, 2, 3 on the principal plane. On the principal shear stress planes, they are like that, and on the octahedral plane, that. And tau, which is the shear stress, obviously on the principal planes. We don't have any shear stresses. On the principal shear stress planes, we have these. So in that slide that I showed you, the principal shear stresses, well, sigma 1, 2 and tau 1, 2, the difference is clear here. Now this is a cubic element, and we got sigma 1, 2, 3, and this is a quadrangular prism element, okay, and as you can see on this plane we have sigma 1, 3 and tau 1, 3, okay, so that's sigma 2, sigma 1, sigma 3, and on this plane also we have tau 1, 3 and sigma 1, 3, and here we have tau 1, 2, sigma 1, 2 and sigma 3. Again, look, this is this plane, okay, that is sigma, that was sigma 1, I think, yes, that was sigma 1, this was sigma 2, this is sigma 3. So on this prism, on the faces, we have sigma 1, 2, tau 1, 2 and sigma 1, 2, and here these prisms, you see, let me just go back to this one. These prisms which we are showing, this face is perpendicular to sigma 2, therefore here we don't have any component of sigma 2, we have only 1 and 3. Here again, this is perpendicular to sigma 3, so here we have only sigma 1 and tau 1, 2, and here it's perpendicular to sigma 1, so on the faces we only have 2 and 3. So tau 2, 3, sigma 2, 3, etc. And here again we have this octahedron, which is isoclinical, means that all the angles are equal. Okay, clinical comes from inclination, and iso means equal. So isoclinical means that the inclination all over the place is the same. We have the same angles, and this sigma 8 and tau 8 are octahedral stresses. Now this is a different element with many faces, and on each face also we have different components of the stress. You need to concentrate on this a bit more. I will put the PowerPoint so that I will upload the file so that you can have a look at it more closely. Okay. This is the three-dimensional stress space, cylindrical coordinates we are using. So we have like this cylinder, the axis is Z, obviously because we have three-dimensional stress space. We have sigma 1, sigma 2, sigma 3, three perpendicular planes, and this Z direction, as you can see, we have written here sigma 1 equal to sigma 2 equal to sigma 3, and we have written sigma m. So it means that this line, which is zeta here, makes equal angles to sigma 1, 2 and 3. Okay, so sigma 1, 2 and 3 are equal for the straight line, OZ passing through the origin and making the same angle with each of the coordinate axes, which in here are these stresses. Okay, let's see what else we have here. Now, the equation of the pi 0 plane is sigma 1 plus sigma 2 plus sigma 3. Before going into that, let me just explain what the stress could be. For instance, we have a arbitrary point P with the coordinates sigma 1, sigma 2, and sigma 3. Okay, that point P in the space is stress space. When we say coordinate, because we have a stress space, so coordinates are stresses, sigma 1, sigma 2, sigma 3, components of stresses along x, sigma 1, sigma 2, and sigma 3, perpendicular to this. Okay. Now here along this z line or zeta line, we have the component of the hydrostatic stress or pressure. Now, as you can see, this is the stress vector OP. On this line, we have divided this OP into two components, one along this line and one perpendicular to this line. So we got zeta here, this is zeta, and this is R. Okay, so and you can see an elliptical plane in here. Obviously we see this an ellipse because we are looking at it from an angle. Okay, otherwise it is a circle. This is a circle, not an ellipse, and we call it pi plane. This equation obviously is the equation of plane. Sigma 1 plus sigma 2 plus sigma 3 equal to 0 is this plane. We call it pi 0 plane. Okay, and this line OZ, which is the direction of the hydrostatic pressure, here you can see sigma 1, sigma 2, sigma 3 are equal. Any plane which is perpendicular to this OZ, we call it pi plane, like this. Obviously here, because the pi plane it has origin or 0, we call it pi 0 plane. So that is the equation of this plane. Therefore zeta is the hydrostatic component of stress, and R is the deviatory component of the stress, which we indicated before. And therefore we could write down sigma is equal to sigma m plus tau m. Okay, that is sigma m, and that's tau m. And zeta is 1 over root 3, sigma 1, sigma 2, sigma 3. This 1 over root 3 is because this zeta makes equal angles to all the three axes. And this R could be written as this from this geometry, okay, because we have the coordinates here. We could write down R equal to that, and also as shown before in the previous slide, R is root 3 tau 8, because tau 8 was this root 3, was this divided by root 3, and it's radical 2j2 and 2 tau m. And for tau m we could write it like that or like that. And also the deviatoric plane, we could show it with this triangle here, which makes equal angles to the three axes, and also is perpendicular to this direction. This direction obviously makes equal angles to the three axes. Okay, so we could write, because this is a deviatoric plane, the stresses on this plane are sigma 1 prime, 2 prime, 2 prime, and 3 prime. And using the geometry here, obviously like that, in this triangle, we could write down sigma 1 cos beta equal to sigma 1 prime, and cos beta is 2 over 3, root 2 over 3. Okay, cos beta 2 over 3. And similarly for sigma 2 prime and sigma 3 prime, we could write similar relationship.